So when we talk of model generalization, we discussed this in a couple of our previous videos. So now we want to look at the concept of bias variance and the trade-off that we have to make. When we say trade-off, it actually means that you can't eat your cake and have it, and there is no free lunch. So there's always going to be sometime you have to compromise some. So especially when it comes to bias and variance, you cannot achieve 100% in any of the two in most cases. So you have to go in between. If you try to avoid variance at all costs, you will move to bias. If you want to avoid bias, you move to variance. So that's why sometimes we have to make a compromise. That's the meaning of trade-off. There has to be a trade-off. You just have to manage to have a little bit of variance, little bit of bias so that you be at the middle. Because unfortunately, for these two big concepts, as you try to move away from bias, you are indirectly moving towards variance. When you try to move away from variance, you are indirectly moving towards bias. So that means you have to strike a balance in between the two and say, okay, this is enough time for me to stop my training. Now, so before we can talk about bias and variance, we remind ourselves again about the concept of inductive learning hypothesis, which says that, basically saying that if the hypothesis work for enough data, then it will work on new examples. Now, we've used that to explain the evaluation of models. What can we do to make our models better? How do we check? Sometimes, no matter what you do, you run into the trouble that your training set performance is good, but the testing outcome, when you test it with new data set, it is not good. We call it overfitting. Sometimes both training set and testing set are not good. That is underfitting. So this is where the concept of bias and variance comes in. If you have too much variance, you're going to leak into one of the problem. If you have too much bias, you're going to lead to the other problem. So either underfitting or overfitting, you're running between the two concepts. And that you have to make a trade-off to make sure that you have the correct thing. Now, so even though you have followed the principle of the hypothesis, if it work on enough data, it work on unseen data. This is what leads us to what we call generalization. See, it is during the generalization process that the concept of overfitting or underfitting or bias variance will come in. So generalization is when you train you expose the algorithm to enough data, which we call the training data, they are labels. So they give them, this is an apple, and you tell your system, this is an apple. See? So after you have done that, this is the training process. My machine learning model, please, can you see this? This is an apple. You say, okay, let me understand the characteristics of this apple and why it is an apple. I'll give another apple. You can see there are little differences. Some of them is the color is a little bit different. It's a little bit oblong. Some of them is a little bit bigger. So we are exposing them to different types of apple. Let them recognize this variants of apple. Then pear, then tomatoes, and so many other things. This is called, once we have exposed them to these different samples, and we also tell the algorithm that this is apple, this is tomato, and the likes. This is called training, supervised training. We are supervising them to gradually understand each of this particular sample. Once you are done with the training, you have exposed it to enough training set. Now we will give the same training set back to the system. But this time around, we won't be showing them the answer like we did before. It's like now I've shown you enough of this training set, and I'm telling you at the same time what they are. Now, the same thing I've exposed to you before, now tell me, can you recognize them? So this is where the concept of training accuracy used to come in. Someone once asked me this question, training accuracy or training performance. So once you have trained your model, the same samples you use for training, you expose it to them again to see that, okay, what I've shown to you, can you really understand it? So sometimes you see them, some algorithm will perform, the new model sometimes perform like 100% accuracy on the training set. Then we say, you don't celebrate with these. Of course, this is a little bit good news that, oh, maybe my model is doing fine. See, once we have 100% or 99%, 100% could be something fishy. But when you get like 95% training on your model, training performance, that's interesting. But you don't celebrate because this is the training performance, the performance of your model on the same sample that they have been trained on. We can say it's not a big deal, but sometimes it could be a big deal because we have seen a model that after training them on enough data, you expose the same training set to them, they couldn't perform. You're going to be getting like maybe 40% accuracy. The same samples they have seen before. So when you see another one performing like 95%, so it's a big deal, but then we don't celebrate until we actually check the generalization ability. This is where we are going. What is the generalization power? Now you are performing excellently well on what you have seen before. This is good. However, if I give you a new sample that you have never seen before, like this one, labels unknown. Of course, we know it, the developer will keep it secretly away from the machine. Now, I now expose this. Since I train you on different apple, can you tell me this? The system say, oh, this is an apple. That's correct. Say this is pear. Oh, correct. He said this is an apple. This is quarter. Mistake. Maybe this correct, this correct. This one is not correct. 1, 2, 3. 3 out of 5. Sorry, 3 out of 6. That is like 50% accuracy. Compared to 95% on training, we can say that this is a kind of overfitting. That is, they are performing 100% on training sets, but they couldn't, of course, 50% is a little bit depend on the area. It's not that okay, but then maybe acceptable in some area, but generally it's not good enough. We can say, but let's say like it's getting like 30% accuracy. Like 30% accuracy, oh, this is overfitting. Something getting 100% in training, but when it goes to testing, it's getting 30%. It means it successfully memorized all the training sample that you have exposed the system to. This is not a good model. So it has run into the problem of either bias or variance, which we want to explain in detail now, inshallah. So this is where concept of generalization led to the issue of trade-off between variance and bias. So what we are looking for is, if you have a model that is getting 95% accuracy during the training, you expose it to the training set again, it got 95% accuracy, and during the testing, it's getting like 75. That's okay. We don't say overfitting, that's fine. We can just do more things to get it better, or it's even getting maybe 92% against 95. That's better. You see, that's okay. You can do more to improve the accuracy, but it's not a problem. It's not an overfitting problem. But when the gap between the testing set and the training set is huge, from 100% to 30%, that is unacceptable. This is a clear case of overfitting, which means that your model memorized the training set. We don't want our model to memorize the training set. We want them to understand it. See, so that they can be able to predict the next one. But often than now, we have this situation. That reminds me of a question I got yesterday from one of my students. He said, the student asked that, is it possible, or there was a case, is it possible to, a question like, is it possible to have a testing outcome that is greater than or equal to the training outcome? That is, can you have like 95% training accuracy and you have like 96% testing accuracy? I say it is possible. Actually, this is what we are looking for, but very rare to have such a case, but it's possible. Where the testing set will perform better, where the model perform better on the testing set than on the training set. This is very rare, but it is possible. And actually, this is what we are looking for. So, but however, if you cannot achieve better training, better performance on your testing set, but don't go abnormally below the training performance. Even you might not even be able to have the same performance for the two. Of course, something that has not been seen before. But you are getting 95% accuracy in training and like 92, 80 something, even 70 something. It's still good. Now, but sometimes the system is not able to sustain this acceptable level. So now, again, to refresh. To check for generalization ability, we already discussed in several of our 4 videos in the past 4 weeks, how you can divide it using 3 options: training, validation, or testing, or using the training and testing, or you go for the resampling method, the one we call the n-fold cross-validation. We recommend this one if the data is not much. And we say this is the one that's better But this is also acceptable. Divide into only two options, training and testing, or you divide into three. So either of the one you use, then the same overfitting, underfitting problem could come in. That is where, because you cannot talk of generalization ability without proper partitioning of your data for training and testing. Now we now ask a question. How do we know if a model is performing well? See, for you to know if a model is performing well, we said the machine learning model performance is considered good based on its prediction and how well it generalizes on an independent test set. So that's why I say you cannot celebrate when you train your system and you check the training samples. There was a student team they were reporting to me the performance of their model on the training set, and they were like celebrating. I said, no, you don't celebrate. We don't actually need training performance. We only check it to be sure our system is not underfitting or overfitting or bias variance problem. Our target is the testing set. That's why, like I told us before, in some of the packages, like Weka we only show you the testing performance. If you want to see the training performance, you have to go to more options and tell the system, show me the training outcome. Then whenever you run the experiment, it will start showing you the training performance. Because originally or ordinarily, people are not that very much concerned with the training accuracy. We want to see the testing performance in reality. Now, so when you check the generalization, this one you are going to check if it is performing. For example, in machine learning, it's actually encouraged that you try to build several models and then compare the performances so that you can select the best, because you cannot really say which of these algorithm is going to work for you. See? So, because nobody can categorically claim that one algorithm is better for all things. In fact, I used to tell people, when you see anybody that tells you that the best algorithm is this, he doesn't understand the basic principles of machine learning. In machine learning, there's no machine learning algorithm that is best for all cases. It depends on the data. And that's why we always tell us the principle of let the data speak. The data will determine which algorithm is good for me, not based on your experience, this algorithm is the best. Sometimes you'll be disappointed. The best algorithm are not perform on a new data set. So, however, when you talk of the generalization ability, for example, you want to predict an election result in some countries and want to see, okay, can you apply the prediction? If you gather data from a particular region, you train the system on that particular data. Can you use the model to predict results from other countries, states, or as the case may be? So sometimes we have errors, which means the model is not able to understand the data to extrapolate, to generalize to unseen data. Of course, this is like an heterogeneous based prediction, which is usually challenging. You use data from different states because they have different capability. Their distribution, their maybe pattern of life is totally different. Now, so how do we know if model is performing well? So you want to check the model is performing well. You assume an input X and apply the function F, which is the model, the trained model now, with the one we call hypothesis function, H. So you now find you do hypothesis function to predict the value, the output, given the input. And now you now find the difference between the actual output and the predicted output. So which we now call the error. And error is actual output minus the predicted output. So, and the error is divided into two types. We have the reducible error and the irreducible errors. Reducible error are error you can play with. You can play with them, you can try to reduce them. While the other one, you cannot play with it. There's nothing you can do. You have to go back to your data set. The reducible error there is known as the bias plus the variance. You can try to play with bias and variance. Try to do more things to make your bias lower, variance also acceptably in the normal way. Make it a kind of trade-off. However, the irreducible error is the one that you cannot do anything about it. There's nothing you can do to your model. You have to go back to your data and clean your data, like noise. Like noise. If there's noise in your data, it's going to affect your performance. It will affect the performance of your algorithm, of your model. So you have to go back and do pre-processing to get your data in the normal shape. That's why they often call it error that you cannot really reduce by playing with your model, but rather you have to go and deal with your data sets. Now, so when you now talk of generalization, that is the capability of your model to generalize to unseen data, we have what we call the component of generalization error. Components of generalization error. The first one is the bias, which is a measure of how much the average model over the training set differ from the true model. This is the concept of bias. Usually, it could be defined as the error due to inaccurate assumption or simplification made by the model. Whereas the variance is how much models estimated from different training sets differ from each other. So that the same model we are doing, if we partition the data randomly different times, are we going to be getting the same thing? Or what is going to be the difference we are going to be arriving at? These two concepts are very important because unfortunately, you cannot have the two to your side at the same time. So you have to make a trade-off. And it leads to two important problems. The first one is known as underfitting. Underfitting. Underfitting is model is too simple to represent all the relevant class characteristics. Quick, just you did a quick fix. Either you're in a hurry, you didn't use the appropriate method, and then it has high bias and low variance. The attribute of underfitting model is high bias, low variance. When the bias is high, that is, it has inaccurate assumption or simplification about the problem being modeled. It's not properly, you couldn't understand that particular data, perhaps due to the parameters that are not well toned, or they are not enough even parameter for that particular model, or it's a wrong model for that particular solution. And again, that was why I mentioned that it's always recommend that we try to use as many as possible models, and then you select the best from them, or use few models that are well known to perform, and then see which one is going to perform for you, because you cannot really tell before you run the experiment which model is going to be better. So when you talk of underfitting, it is characterized by high bias and low variance. So to make you understand how you visualize it when you work, it is having high training error and high testing error. So when you train your model, finally, you are getting something like 30% training set and then 25% testing set. This is an underfitting problem. It means your model is not able to understand even the training set, not to talk of testing set. If your model couldn't even understand the data set you have exposed it to, how do you expect the data, the same model, to perform on testing set, something it has never seen before? This is practically impossible. And this is the characteristic of underfitting. So when you run your model, you're getting testing accuracy of 30 or 40. Quickly go and look at the training accuracy, the training performance. Is it low? If it's also very low, then this is underfitting problem, which means you have high bias, low variance, which is characterized by high training error and high testing error. You know, when we say, not to be confused, you know, when we say high testing error, if you have 30% training accuracy, that means you're going to have 70% error. That's why we say high error. If you have 25% testing accuracy, it's going to be 75% testing error. So the higher the error, the lower the performance accuracy. So, and the opposite holds in case the system is good. The second problem that bias variance could lead to is what we call the overfitting problem. Underfitting is fairly easy to detect because once you see your model not performing well, you check the training accuracy also, the two of them are bad. You know that, okay, either my model is not able, the algorithm I've selected is not able to model this data properly, or I need to do more tuning the parameters and the likes. You can easily figure that out because your testing accuracy is not, the training accuracy is also not good. Something that's not good for what it has seen, you don't expect it to be good for what it is. Something that's not able to predict correctly for what you have exposed it to, it's definitely not going to be able to perform for the unseen data. So for overfitting model, this is overkill. You see, the opposite of underfitting. Underfitting took it too light. Life is easy. Just fix something for me. It doesn't work. But this guy is again, in order to avoid overfitting, it ran into trouble. The model is too complex and it fits irrelevant characteristics or noise in the data, unfortunately. So this is overfitting. So let's say, for example, we are fixing a model here. We want to, there's a model, small model we want to build. So this is the training set. This is the training set. So I better fix a model like this and leave this data out than to have a model. This is like this. I fix everything. Even this, I fix this. And I go here, I fix this. Because these guys, these are outlier, these are noise. Our model should be able to ignore those kind of data because there's nothing they can do. Otherwise, they're going to go into overfitting. So when you make your model too complicated, too complex, you try to understand every data set. Some data sets are just out of range. We need to ignore it. And that's why pre-processing also is very important. So in an attempt for your model to make sure that I take care of every samples that I'm exposed to, I need to understand all of them. The system ended up memorizing the training set. And when the system memorizes the training set, there's no way it can work on testing sets. This is the problem of overfitting. Now, and it is characterized by low bias. Let's pay attention to that. Low bias, high variance. You can see this opposite. Underfitting is high bias, low variance. So you want the guy, it was having high bias, low variance. It tried to reduce it. As you are trying to reduce the bias, it went into high variance, unfortunately, because they're on the opposite side. When you are running away from high bias, you are going to high variance. When you want to run away from high variance, you are going to high bias. That's why we have to make a trade-off. We have to stop in between. You cannot achieve zero bias. So you cannot achieve zero bias. See? Because you want to get better results. You are going to lead into overfitting. So you have to stay in between the two. That's the point to stay. How do you know where to stay? We are going to get there and we are going to see. In a layman words, how do you understand that there's overfitting in your work? The easiest way to quickly understand there's overfitting in your work is you're going to have low training error and high testing error. You can see. Pay attention to this. This can confuse people. Low training error means the performance accuracy is going to be high. You know, when you have low training error, it means here it's like you're having like 99% accuracy. So the error is just 1%. Very low. But when you use testing sets, this is for training set. When you go for testing set, you are getting just like 45% accuracy. And then which means you're having 65% error. That's high. So this is called overfitting. Low training error, high testing error. Why it is more challenging to detect is a lot of people, they pay attention to the training accuracy. Once they run their model and they're getting 99% accuracy, they start celebrating without testing the model. I said, don't jubilate with training error accuracy. Until you check it on your testing set and you're getting reasonable results, then you can celebrate. But before then, there's no celebration because you could be suffering from, your model could be suffering from a problem called overfitting problem. So you have to avoid these two. You don't want underfitting. That one is easier to detect before everything is not going to be good. It's going to be a high training error, high testing error. But for the overfitting, you're going to have excellent training accuracy, very low error. Sometimes you can get 100%. You can get 100% accuracy in the training. But by the way, once you get 100% accuracy in your training, you start praying that, oh, I hope something doesn't go wrong. Quickly bring in your testing set to check. Then you got 99 also in testing set. That's a celebration. Or 98, 95, even 85. That's still good. You see, because we rather have a model that can compromise during the training set and get good result for us. I would rather have like a model that is getting 95% accuracy in training set, and getting like 95 or 94% in testing, rather than having a model getting 100% for training and getting 95 for testing. Because our own interest is the testing, the one you have never seen before. This is what we are interested in. So there is a way you can train your system and trying to see how you can ensure that it doesn't go to extreme level. So for the bias, which is, I say, reducible error. So error you can play with, you can do some things we are going to suggest to you as we move on. So here the average predicted value are far off from the actual value. See, you can see this is high bias, low variance. See, this is underfitting. So we want our prediction to go to the center here. This is what we are looking for. At least you should be inside there. You can see everything is concentrating outside what we are looking for. So it's not good for both training and testing. This is what we call bias. So model with high bias, they pay little attention to the data and oversimplifies the model. You see, they pay little attention to the data set. It's like overconfidence on the side. We can see overconfidence. Oh, this data, there's no big deal. I just do it quickly and go. At the end of the day, they messed up the model because the model is not able to perform even on those you have exposed them to. If they cannot perform on those you have exposed them to, what is the miracle that's going to make them to perform on the one they have never been exposed to? So it always leads to high error on training and high error on test data. So, and it's because the model is too simple and doesn't capture the complexity result. It doesn't capture the complexity because your model must be able to capture the relationship within the data set. Sometimes the relationships are so complicated. And that's why sometimes you might not be able to get a single model to do that. You might have to go for ensemble if the data sets are really complicated. This is the effect of bias. You have now, the next one is variance, another reducible error. That is, you can play with it. So you can try to improve your model on it, unlike the noise that you have to go back to your data set. Treat your data to get rid of that. Now, in variance, we say the amount by which the model prediction will change if we estimated using different training sets. So model with high variance pay a lot of attention to training sets and doesn't generalize on data which it hasn't seen before. See, they pay too much attention to the training set. That is another extreme. The previous one was not paying attention to it properly, but this one goes to the extreme end. I want to understand every data set. In machine learning law, sometimes you need to allow some data set to be missed during the training. That is the compromise. That is the trade-off. You better get 95% accuracy during your training than getting 100%, and then your system cannot understand new data set coming. Because you are trying, when you are getting 100%, it's like if there's a noise in that data, you are trying to fix the noise. Your data will be taken outside the range. And when new data comes, you won't be able to capture it. As I'm going to show you in one of the I'm going to show you a kind of illustration shortly. So as a result, such model perform very well on training sets, but has high error rate on the testing set. And like I said, there's nothing to celebrate in getting high training accuracy, while the testing accuracy is very bad. So this is high variance. You have high variance and then low bias. This is the characteristic of this system that has overfitted the system. Now, so when we put the two together, bias and variance, so what do we go for? You see, overfitting has good performance on the training sets, but poor result on testing data. Underfitting, poor performance on the training data and poor performance on the testing data. Either way, this is bad. This one also is also bad because we are more interested in the future prediction, the generalization. So we say bias causes underfitting. When you have high bias, it leads to overfitting. When you have high bias, it leads to overfitting. This one, bias causes underfitting, whereas variance causes overfitting. Unfortunately, we don't need any of these two. So what do? Then we have to make a trade-off. So we have to make a trade-off. You have to train and stop at some point that is good for you to stop before it goes into overfitting. So don't overkill, don't overtrain your system so that you don't lead to overfitting. And don't undertrain it so that you don't need to underfitting. This is where the concept of trade-off between bias and variance and the generalization. Now, we say the Bias-Variance Tradeoff. Now let's look at the two examples now. Let's pay attention to illustrate the concept. Yeah. In the bias-variance trade-off, we look at this model. These are data points. These are data points you want to use to train, to develop your model. These data points, you can see we have somebody who is just, maybe is in the east, or the model doesn't, or the algorithm is not the appropriate one for this data. This is the model selected. This one is blue. You can see just a line. Oh, I'm done. I'm done with my modeling. Your model, look at the data here, is able to capture just very few data points. We say model with too few parameters. They are inaccurate because of a large bias, not enough flexibility. It ignores a lot of data points. That is why it's not performing on the training set. If it doesn't perform on training set abysmally, how is it going to perform on the testing set that we have not even seen before? So that is why models with too few parameters, they have high bias, they are very underfitted. They took simplistic view of the data set. Life is not difficult, just deal and go. You can lead into underfitting, which is the high bias. However, when you see someone that is doing that, oh, in my own case, I'm not going to do it. I need to follow the data point. Look at what this one did again. This one said, okay, this is the, I don't want to miss any data point. So you can see this is the model. This one in blue. It's trying to pass through close to every data point. See? Now, this data is going to overfit. Now, before I move to that, let's go back to this number one. The ideal model is this color. Can you see this color? I hope it's showing. This is the ideal model. The ideal model is like this. You can see this is the correct model. It's not going to every data point. This is like asking in a bus that used to take kids to school. You say some kids together in some garage, in some bus stop, or every three houses, let them meet here or something like that, so that we can get to where we are going at the appropriate time. But you need to follow everybody to their houses. Some are staying very, very far inside. You ended up taking the kids to school at maybe 9:30 in the morning or 10 a.m. They already missed a lot of classes. You see, that's you have to in between. You don't ask kids also to go to big garage where there's going to be a big problem for them. But at the same time also, if they are told do too much decentralized and you have to go to everyone's house, you're going to lead into trouble because there's going to be delay. Except you want to bring in more buses to take the kids, which is like ensemble now. You see, several buses, let them pick the kids, you can still solve the problem. But you want only one bus to solve this problem by picking kids from their houses, and they have to pick like 200 kids. And you don't want them to get late to school, it's impossible. This is a very big analogy I used to give when it comes to the issue of bias variance. So in the bias case, you can see it's too simple. You see, it doesn't care about where the kids are located. I'm going. If I pick you, pick three guys, I'm gone. So it's not good for the training set. It's not going to be good for testing set, for sure. The correct model should be like this. You can see, not too simple. You can see there's not capturing all of them, but if the next, during the testing, let's say the one data is here. Let's say one data is here. During testing, this is the testing set, comes here. You can see this model can easily understand because it's closer to the model. If one is here, it can see it. If one is here, it can see it. This is the advantage of having a very flexible model. These are testing sets that are thrown into the space for checking. But look at this straight line. You can see that it's far away from this. It's far away from all the new samples. In fact, all the new samples might be coming from here. Which means this model that is normal, that is the ideal model, will be able to identify these new samples. But for this underfitted model, it will not work. This is how underfitting is a big problem. Now, to solve that problem, some people, again, they overdo. They go to extreme, which leads again to overfitting. And what is overfitting? You try to go to every data. You have to match every data. No, this is overkill. This is too much. Rather, the ideal model is what we have told you. This one is the ideal model. Just go through it. You can miss some samples. So this one could get like maybe 85% accuracy. during training, but you can be sure that in the testing phase, maybe it can also get like 83% accuracy, which is acceptable. But then we can try to improve it later. But this one, you can be sure this blue guy, because it's so close to those guys, it's going to be getting like maybe 98% accuracy. But when new samples comes, maybe these new samples are here. They are all here. These new samples are here. Unfortunately, when you have new sample, this guy has gone down to locate one data here. And now new sample comes here, it's not able to locate it because it's far away from that sample. Another new sample comes here, this guy has gone up again. Another sample comes here, this guy has gone up. So when you want your model to locate, to memorize every data, it takes them away from the appropriate location where they can be able to capture new samples that are coming in. So this is the idea of overfitting. So your system is following the data to their location, even if this data, maybe this is an outlier, it's following it up there. That's not correct. This is called overfitting. Here we see models with too many parameters, they are inaccurate because of a large variance, that is too much sensitivity to the sample. You want to memorize the sample, and when you have new sample, you will not be able to model it appropriately. So this is a case of overfitting. Why this is a case of what? Underfitting, which is high bias. Why this is high variance. So what do? When we are training our model, we train in such a way that we don't go into the high variance, but we stop at a particular reasonable time before it goes into overfitting. Because you move from left, you move to right gradually. As you are moving, you're actually moving closer to overfitting. So you have to know, where do we stop? At what point do we stop that is okay for us? And at what point do we continue that is still fine? Now, so what do we look for to really achieve in this concept? Low, we can have, these are possibilities. We can have low, which we call moderate bias. We have moderate bias and moderate variance. Is this achievable in reality? Yeah, this is what we can look for actually. We said this will have been the ideal situation. So the error of prediction should be as less as possible. Here, models are accurate and consistent on averages and still perform acceptably well on different data sets. So we can try to see, okay, can we have moderate bias? Because you cannot kick bias out. You cannot kick variance out as you've seen it. You move away from one, you fall into the other. You move away from another, you are back to where you are running away from. So you have to know when to call it a day when you are training your model. And some of the methods and suggestions how to avoid overfitting, how to avoid underfitting, we're going to be mentioning them as we move on in the presentation. So we can also have another scenario we might have is low bias. It's low bias, high variance. Low bias, high variance. You know that this is overfitting. It happens when our model captures the noise along with the underlying patterns in the data. It happens when we train our model a lot over noisy data. Here, models are somewhat accurate but inconsistent on the averages. So that a small change in the data can cause a large error. So this is the challenge with it. So when you have low bias, high variance, it means you try to memorize your data set, which is really, really dangerous. So in so doing, we have to try to see, but at what point can we cut our training? What can we do? This kind of problem are well noted for some methods. For example, neural network, which is one of the very popular methods, is prone to overfitting. You can train neural network, you can get 100%. When you put a testing set there, it doesn't perform. Of course, there are a lot of variants of neural network now that are trying to solve this problem by putting some point to check. At what point do we stop? Because it is actually greediness that makes our model to go into overfitting. So we need to put a point in an attempt for that our model to minimize the error. Because the idea of training model is we want to minimize error on the training set, with the thinking that if we are able to minimize the error on the training set, we can perform on the unseen data set, which is a good concept. But sometimes while we keep minimizing, there's a point to stop. You don't need to really get to zero before you stop. At what point are we going to stop? What are the deciding factor? And what are the actual trade-off that we're going to make between the bias and the variance? So some of these questions, by the grace of God, we are going to answer next week because of time. So this is where we're going to call it a day. So we'll be completing the remaining part of the bias variance trade-off based on the concept of generalization next time. Thank you very much. So if you have any question, we're going to take a few questions before we call it a day. Thank you very much, and you're welcome.